Hey, what's going on, guys? Kinsey here. In this video we're going to be programming Banator's 8-bit breadboard computer emulator in Python. So just a few words on the hardware that we're supposed to be emulating. So there is a fantastic guy, his name is Banator, has much more subscribers than I do, good for him. And he made this absolutely tremendous, I believe the best in the world series on electronics that one could have ever imagined if he wants to start this absolutely from scratch. So this is now building an 8-bit breadboard computer, and the end result of this series looks like this. So you probably, if you're watching this video, then probably you've been through this series, at least some of the videos. So just a few words like what the system is this. So it's sort of a TTL logic gate system that allows to perform very simple computations. So it doesn't have a CPU as a single chip. Instead, it has all of these modules being split into smaller integrated circuits. I'm complete noob in electronics, so it's really hard for me to describe how exactly this works from the perspective of the electronics. And what we're supposed to be building here, what we're supposed to be writing, is a sort of a high-level abstraction. But this high-level abstraction, even though it's not going to be a circuit level emulation, obviously, but still, those programs that are written in Banator's assembly are assumed to be running on the emulator that we're supposed to be making here. And well, there would be the difference, obviously, because the original computer can output the data as the digits, only digits on 3 7-segment LEDs. So we're just going to be outputting this the result to the console. But this doesn't matter really that much, because the reason, now just a few words about the reason why to actually make this. So when I was originally I was looking for a way to write a 6502 CPU emulator, but that's way more complicated. And in order to have a clear understanding of how the CPU works, and what is the bus, the 8-bit bus in particular, and how the objects that are organized around the bus are interacting with each other. So in order to understand all these concepts on a hardware level, like what's the clock and how clock allows you to synchronize all the stuff all together, in this case, this series is really the best ever. And this helped me, even though it's completely about electronics, it helped me to really start understanding how to write the software that emulates the hardware. That's absolutely essential. So I can't point exactly like which chip does what in particular. I just can say that it has 2 general purpose registers A and B, for performing arithmetic operations. So that's what it can do. It has only 16 bytes of random access memory. It has the instruction register holding current instruction to execute, where the upper 4 bits are the opcode and the lower 4 bits are the data. And all the opcodes and data, like the program itself and the data, they all are shared within this 16 bytes of program memory. Also, it has a carry flag to keep track if we are exceeding the 2055 value, like FF above or below 0, when we are performing those arithmetic operations. The 0 flag is also on the cards, and so-called halt flag, which flags the end of the execution. Also, it has the program counter, which is 4-bit basically, and counts from 0 to 16, because that's the entire addressing range that this particular hardware supports is only 16 bytes. So you can address only 16 bytes of memory, because that's the hardware limitation for program counter. And you might be wondering that you can't do much with this sort of a setup, but I highly recommend to learn how this computer works, because in this case, if you can understand how this works, and if you write an emulator for this computer, then you can write an emulator for really whatever, because this gives you the structure, the bare bones, and then you can just add some meat on top of that, so add some flash basically. So yeah, that hopefully would be making some sense. So in this video, high-level implementation of Beneder's computer in Python. So without further ado, let's actually start. We don't need, I don't need a web browser anymore, so let me just close it. And the only thing we're going to be referencing to complete this is the list of the supported opcodes. And here are the opcodes themselves, the mnemonics. Probably I'll make another separate video creating an assembly to assemble Beneder's assembly language into machine codes, into binary basically. But that, yeah, it's just going to be too much for one single video. I just want to keep it tight, as tight as possible. Right, but this should be literally enough to create the entire emulator. So I would just start writing the code. I would be trying to talk through the code, like what exactly each particular data structure does. So it would be really practical, and hopefully this approach makes sense, because I'm not ever trying to explain how Beneder's computer works from the electronics perspective, because I'm not in electronics, but hopefully you'll have a clear idea from the programming perspective how it works, like from the programmer's point of view. So without further ado, let's actually start. So we'll start by defining a class of this 8-bit breadboard computer class, and let's just call it breadboard computer, like this. And now here to initialize constructor, we want to have def init, and it takes the self instance. But here I just want to call reset CPU, because I just want to have the separate function for resetting CPU. So here I just say self dot reset, and like this. Yeah, this should be fairly enough. So here we'll provide a function to reset the CPU, and meanwhile this function, so let's call it reset. Yeah, just reset should be enough. It also takes the self instance. So here actually we'll start defining all the data structures we need. So let's start with the register array. So this is gonna be self.a is equal to 0. So this A register is an 8-bit register, which means it holds an 8 bits at a time, 8-bit, right? Then register B, it's also 8-bit, and I say self.b is equal to 0. So I'm doing two things simultaneously. I'm initializing the inner classes of the breadboard computer, meanwhile resetting them. So just easier to make it like so. Then we have the instruction register. It's also 8-bit, and it holds the next instruction to execute by the computer. So self.ir stands for instruction register, equals to 0 as well. Then we need a program counter. So let me just make it like this. So program counter. So program counter is essentially an iterator over the entire addressing range, which is in our case only 16 bytes, sorry. So self.program counter, and yeah, program counter is 4-bit. Just counts from 0 to F. That's all it can, and it's gonna be equal to 0 as well. All right. So also we need carry flag, 0 flag, and the hold flag, right? Yeah, and the output register as well. So here, let me just send this output register. So this, let's call it self.out is equal to 0. So this is just used, this is the hardware kind of register, it'd be registered to then take the data from it and decode it to output on the 7-segment, on 3 7-segment LEDs. So literally the result goes into this sort of a register or variable. Okay, so here we have the 0 flag. So I'm not just define it for now, and then when it comes to the implementation, I'll explain how it works. So self.zero flag is equal to false. So this is kind of 1 bit. So it's gonna 1 bit, right? And then we have the carry flag. It's also gonna be 1 bit here, right? Self.carry flag. So would it be equal to false by default? Oh man, it's Python. We shouldn't really. I shouldn't have. I don't really have this. Sorry, guys. We don't need the semicolons in Python. Sorry. All right, and in the very last but not least is the halt flag. So which flags when the execution ends. So self.halt is equal to false. Oh, sorry, false, like this. All right. Now let me just say Python 3 breadboard.py to make sure it compiles. Okay. And probably the next thing I want to do here is to what's wrong with my mouse? I want to provide the debug, sort of a debugging function. So print debug info, and here def, let's call it debug like this, takes the self instance. Here I just want to print all we have. So let's say register A, and here self.a, and then register B and the B register, then what else? Output, register output, and the output instruction register, and the program counter, and zero flag, and carry flag, and last but not least the halt flag. Okay, so now we can create a big computer, big breadboard computer instance like this. So let's call it computer equals to breadboard computer, right? And now if I say computer, so by the time it's initialized, and it calls this init automatically, so it should call this reset, and after we should be able to see all the internal fields. So it should be referenced like really computer.a, computer.b, computer.out. But as far as we have this debug, it should be fairly enough. So we can't call reset explicitly. We cannot do it. Doesn't matter. But anyway, I want to say computer.debug. And if I did everything properly, now it should print. Yeah, it does print all the values. But there is one more important thing that we need to add to our computer, which is the random access memory. So self.ram is going to be equal to, so initialize 16 zeros here, because we have up to 16 bytes. So we have 16 bytes of RAM. And also here I want to print RAM and self.ram. All right, so now we have all the values for our RAM. It's probably would be a little bit more easier to print them in hexadecimal. So here I can simply say it like this. So hex and I for I in RAM. So now we have this hexadecimal values for whatever we have in the random access memory. And actually, I believe that it's also a good idea to have this hex for the rest of things. Yeah, should be actually this should be binary. Okay, this should be binary. This should be binary as well. So hex. Yes. Okay. All right. Like this. Okay. So yeah, we have binary for 0 flag, for carry flag, for hold flag. The rest are this hexadecimals. So far so good. So this is great, and now we are ready to provide the main loop here. So main loop, and just create in def run, takes the self instance, and here well, we can actually put this initialization into the run, but yeah, maybe let's not do it. So run program from RAM, and while not self.hold, so until we have the hold flag being set to false, what we actually do here, so first we want to initialize instruction register, and we just simply say self.instruction register is equal to self.ram indexed by self.program counter. Then we want to execute current instruction. That's simple. So self.execute. We don't yet have this, so I just commented out for a while. And here we want to increment the program counter. So self.program counter plus equals 1. And yeah, this should be fairly enough. And for now, just for debugging purpose, well, actually, yeah, let's actually start defining our execute here. So execute opcode is the main is the core of the entire CPU emulator. So def execute. So it takes the self instance, and here first thing we want to do is to extract opcode, and just to give you an idea, so the first 4 bits do represent the opcode, and the second 4 bits do represent the data that goes as an argument for that opcode. So opcodes might have or might not have the arguments, and this depends on this opcode list. So for instance, nope doesn't need to have the kind of argument here. However, the LDE that loads contents of a memory address, whatever, into the A register, for this one in particular, it actually needs to occupy the lower 4 bits in order to specify the argument that is supposed to be taken by this instruction. So in particular, the address itself. So as far as we only need 4 bits to represent this 16-byte address, that literally not, because that would be either from 0 to F or from 0 to 15 if we're talking about decimal. All right, so I hope it makes sense. Here we have like opcode and argument. All right, so yeah, hope it makes sense. So we need to extract this one and then shift this to the right. So yeah, I'll now show you this. So format is so this is instruction register format is the following. So we have the opcode followed by the argument. Okay, so let's say opcode equals to, we take self dot instruction register, and we need to bitwise AND it with hexadecimal F0. So the first four extract the first 4 bits, and then right shift this to 4, and this is how we have the opcode. And for argument, the problem is that we could have since not all the instructions have the argument, it might not be that necessarily needed to have this. But anyway, I think we can, for now, extract argument. If this code doesn't work later on, I'll just change it. So argument, it's not always gonna be on the cards. Like for NOP operation, it's not always on the cards. So here I just say self.instruction register, bitwise ANDed with direct 0f. So the lower 4 bits, right? And here, let's go the following way. So I just want to print, so this is just for debugging purposes. So opcode, and we go in for opcode, and then argument, and argument like this. So let's try to run the code to see if it works at some point. Okay, so I just didn't yet, so just print the debug. Probably don't need this. So I just want to say computer.run. Okay, and here we go. So we're starting iterating over the RAM. And also, I also want to print the program counter because that's also essential. So program counter, even though it's available within the debug, but anyway, I just want to make it separately. Self the program counter. All right. Yeah, this should be the case. So yeah. So first program counter is equal to 0, so it literally points to the very first element in the RAM. Then it gets incremented. So then this one, then this one, then this one, and so on. And we have the opcode and argument being equal to 0. Yeah, one more thing to consider. So let's consider hexadecimal. It's just better to see this visually in this case. And don't get confused by this error, since we just run into the exception because we don't have the hold being activated. And on the other hand, the problem is that we run out of the elements of the RAM, so we're just running out of the RAM. So probably one of the simplest way of doing this is just to wrap this with the try except. So I can simply say try here and here except, and just can print. Let's just say all done. And I think, well, it's not the best ever exception handling, but it's at least this is better than having the error. So I think this should be just working nicely for now. All right, so we have our program counter iterating over the indices of the random access memory, which is good. And also we have the opcode and argument extraction. But since we have all the 0 values there, it's not really easy to see how exactly the extraction happens. So just to give you an idea, so probably in the init, I believe this might be done in the init. So say load program into RAM. We can then later add the logic to load the program from the file, for instance. But for now, I just say self.ram 0 is equal to, let's give it a value. Now it doesn't matter which one in particular we're going to be given. Well, for instance, yeah, let's go like 1 for LDA and then the value. So 1 and the value, let's say E, for instance. And then just to give a few just to write a simple program which doesn't do anything useful at the moment. But anyway, so LDA, then for instance add, this is going to be 2, so this is going to be 2, and we add the value from loads contents of a memory address into the B register, then performs A plus B. Yeah, let's take it from, for instance, from A, and here sub 3, so this is going to be 3, and from the location F, just for instance. So if we now run this, okay, I'm just wondering why this didn't this should have didn't update the memory for some reason. It's a little bit strange. Okay, just self dot. Yeah, here we have this update, but then it gets lost for some reason. This is a little bit strange. This is a little bit strange. Well, probably, yeah, let's do a little bit different. So load program to RAM. So def load takes self as an argument and put it somewhere like here. Okay, so just hard code something here, then we can add logic to take this program from the file. Okay. So reset, then computer.load. It might be taking argument later on, but for now this should be just fine. And let's have a look. Yeah, now we do have this RAM being updated. All right. Okay, yeah, fine. So now we have these values in the random access memory. Now you see, like, we do take the first 4 bits, which in hexadecimal is represented by a single digit. Single hexadecimal digit represents 4 bits. This one represents 4 higher bits. This represents 4 lower bits. So we have the opcodes instruction. So 1, this is it. Then 2, this is it. Then 3, this is it. And then the values, the arguments. So argument for this opcode is E. So this is this is it, right? Then A. So these are the addresses. Then A, and here we have F. So here it goes. So I hope it's clear. And now we can make a sort of a switch case statement. Well, we don't have switch case in Python, but the principle still applies. So we can just distinguish the opcodes and what in particular do we want to do with our internal registers and memory, depending on the description of the current given single current given opcode. So at this point, I believe that we already can start actually implementing our instructions. But yeah, probably just to avoid this video being too long, I'll probably stop here and continue the next video. So this is it from my side. Thanks for watching. Until the next time, and take care.